Yeah, good afternoon, students. I welcome you all to the session. So I hope you all are doing good and safe. So I'm launching a poll. So just let me know if I'm visible and audible to all of you. Only one has responded. What about others? Am I visible and audible to all of you? Valmiki, Shreya, Yashwant, Bishan, Anusha Patel, Anil. Can you all able to hear my voice and can you all able to see me? So I have launched a poll. You can give your answers over there. Okay. So now let's go for the session. So yesterday we have discussed about the valence bond theory, right? And some part of isomerism we have discussed. And in valence bond theory, we have studied the introduction to valence bond theory and some complexes, some octahedral complexes and some tetrahedral complexes we have discussed, right? We have discussed the hybridization, magnetic nature, and the geometry, and what else? The magnetic moment and the type of complex, right? So all these things we have calculated and we have found out for octahedral and tetrahedral complexes. Now we are left with square planar complexes and at last the limitations of VBT. Okay. So now let's go for the square planar complexes. So coming to the square planar complex. So the example that we are going to take is, just give me a second. It is a nickel complex. Okay, it is a nickel complex. So the configuration for nickel is 3D8 and 4s2. Okay, and for nickel 2 plus, it is 3D8 and 4s0. So now what will happen? Since a strong field ligand, if I take NiCN, if I take NiCN 4 times 2 plus, it is not 2 plus, it is 2 minus. Okay. So if I take this complex and here the oxidation state of nickel is 2 plus. Okay. Oxidation state of nickel is 2 plus. And this CN minus ligand is a strong field ligand. Yesterday I gave you the list of strong field ligands, right? So it is a strong field ligand. So electrons will get paired up. And this will lead to this type of configuration. Okay. So now one d orbital is empty, one s orbital is empty, and 3 p orbitals are empty. So now these 4 ligands, what they will do? They will come and occupy the hybridized orbitals, right? So 4 orbitals will intermix with each other. D, S and P2 will intermix with each other and they will give DsP2 hybridized orbitals. Now to these 4 DsP2 hybridized orbitals, the 4 ligand, the Cn minus ligand will come and form the bond. Okay, and they will occupy these 4 hybridized orbitals leading to this configuration. Okay, so the hybridization for nickel tetracyanide complex is DsP2. Okay, and the geometry is square planar. If it is DsP2, the geometry is square planar. All right. Now coming to the metal configuration, it is 3D8, right? But all the 8 electrons are paired. So there is no unpaired electron for this complex. Okay. So since all the electrons are paired, what is the magnetic nature, my dear students? Is it paramagnetic or diamagnetic? Is it paramagnetic or diamagnetic? Can you tell me whether it is paramagnetic or diamagnetic? Very good. Very good. It is diamagnetic, right? So, 0 unpaired electron. So, it is diamagnetic in nature. If it is diamagnetic, then the magnetic moment mu value will be equal to 0. Okay. Hybridization is dsp2. Geometry is square planar. Magnetic nature is diamagnetic and the dipole moment is 0. For all diamagnetic complexes, the dipole moment will be equal to 0. Okay. So this is all about the nickel tetracyanido complex. So any doubt for anyone? So is it clear for all of you? Let me know your answers in the chat box. Please feel free to give your answers. Yes. Okay. So now we'll go for one question. So we have completed all the complexes, taking some examples for each, and now I'll go with one question. Predict the number of unpaired electrons in square planar platinum tetracyanido ion. So can anyone find out the answer for this question? You need to find out the number of unpaired electrons in this complex. So to find out the number of unpaired electrons, first of all, we need to find out the oxidation state of the metal, right? So what is the oxidation state? It is coming out to be +2 because for platinum, it is X. Each Cn will have -1 charge. So there are 4 Cn. So it is -4, which is equal to the charge on the complex -2. So X is equal to -2 plus 4 is giving +2. Okay, X is equal to +2. So platinum is in +2 oxidation state. Now, what is the electronic configuration for platinum? Can anyone tell me the electronic configuration for platinum? Or tell me to which group the platinum belongs to. If you find out the group number, you can find out the electronic configuration. It will be easy. Can anyone give me the group number of platinum? Or the first member of the platinum group? Who is the first member of the platinum group? It is very easy actually. It is nickel. Okay, so platinum belongs to nickel group. Nickel, palladium, and platinum. Okay, so nickel is a 3D element and palladium belongs to 4D series. Platinum belongs to 5D series. Now, what was the electronic configuration given to nickel? It was 3D8 and 4s2, right? For palladium, it is 4D8, 5s2. Then for platinum, it is 5D8 and 6s2. 5D8 and 6s2 is the electronic configuration for platinum. Okay, so here is the diagram. Got it? Now, since platinum is in +2 oxidation state, we have to remove this s electron. And if we remove the s electron, we will get this type of configuration. And now what we have to see? We have to look into the ligand. So we have Cn minus ligand, which is actually a strong field ligand. So what will happen? Pairing of electron takes place. So the two unpaired electrons will get paired up with each other and we will get this type of configuration. Now, the orbitals used for hybridization is D, S and P2. So they will give dsp2 hybridization. But while coming to the unpaired electrons, it is 0. Okay, we don't have electrons, unpaired electrons in the 5D orbital of platinum. Okay, so the answer is 0. So is it clear, students? Any doubt for anyone? So what you need to do, at least for some groups, you need to study all the elements. Okay, like nickel group, copper, silver, gold will be there. And zinc group, zinc, cadmium, mercury. So for certain groups, you need to memorize the first three elements. Okay, 3D, 4D and 5D element you should memorize. So then only it will be easy for you to solve this type of question. Clear? Okay. So now let's go for the last topic of this valence bond theory, which is the limitations of valence bond theory. So what is meant by limitation? Disadvantages, right? So the first disadvantage of this valence bond theory is it involves a number of assumptions. So scientists, what they did, they assumed many things. They assumed that ligands will come and form the bond with the hybridized orbital of metal. So that is actually the assumption. Okay. So they did not prove it. They did not have any experimental proof. So it was their assumption. So like this, many assumptions were involved here in this theory. Okay. And here in this theory, there was no explanation about the color of the complex. So we did not study anything about the color of the complex in this, right? Because in all the coordination compound, if you see, we have the central metal atom. That central metal atom is a D block element. So mostly the D block ions will show color. Okay, but here there was no explanation about the color in this theory. So that becomes the second limitation. Thirdly, it does not give a quantitative interpretation of thermodynamic or kinetic stability of the coordination compound. So valence bond theory did not tell that this particular complex will be stable for this particular time. So it will be stable for half an hour. It will be stable for a long time. It will be stable for this particular day. So the stability information, the thermodynamic and kinetic stability information was not given by the valence bond theory. Okay, because some compounds, if you see, they will get decomposed. If we heat the compound, it will get decomposed because it won't be stable. Okay, so such kind of stability, thermodynamic or kinetic stability were not explained. Got it? And it does not make any distinction. Distinction means the difference between the strong field ligand and weak field ligand. So, it means, like for example, it did not say that why manganese hexacyanide form inner orbital complex, manganese hexachloride form outer orbital complex. So we have two manganese complex. We have two manganese complex. One is having Cn minus as the ligand. Just give me a second. Yeah. So sorry for the interruption. So in one complex, we have Cn minus ligand and in the other complex, we have Cl minus ligand. Cn minus forms inner orbital and Cl forms outer orbital. So this we know, but it did not give any explanation that why Cn minus is a strong field ligand and why Cl minus is a weak field ligand. Okay, so no explanation was given for strong field and weak field. Okay, so all these are the limitations of valence bond theory. Okay, so because of this limitation, the third theory, which is called as crystal field theory, has come up with certain postulates and with certain concepts. So that we will see in the upcoming slides. So before moving on to the crystal field theory, I just want to give you a question. Okay, a very easy question it is. So let's do this and then we will go for the crystal field theory. Okay. So the question is, among the following ions, which one has the highest magnetic moment value? So there are three complexes given to you and you need to find out which one has the highest magnetic moment. What is meant by magnetic moment? The mu. So mu value we need to find out. So the one who will have the highest magnetic moment value, students, the one which is having the highest number of unpaired electrons will have the highest magnetic moment, right? So you need to find out the number of unpaired electrons for all these atoms, metal ions. Okay. So all the three has water molecule as a ligand. So no issues. We can find out the answer so easily. So which among the following has the highest magnetic moment? So some of you have got the answer. Is it option 3? Option 2? Say any one. 2? 2 or 3? 1. Jabrun is saying 1. Bishan is also going for 1. What about others? Let's go for the majority. 2, 2, 2, 2. JNV Anam is going for 2, 2, 2. Okay. Christina Priyadarshini is going for 2. Rikanya is going for... So what is this? Many of you are going for 2 and many are going for 1. Some are saying 3 also. See. 1. Yamarti is getting 1. Okay, let's see. Let me start with the first complex. So this is chromium. What is the oxidation state of chromium here? What is oxidation state of chromium here, my dear students? Yeah, it is 3. Right? Water is a neutral ligand, so no charge. So it is just, oxidation state is just equal to the charge on the complex, which is 3. Very good, very good. Oxidation state is 3. So the configuration of chromium is 3d5 and 4 is 1. And if we remove, this is the configuration of chromium, 3d5 and 4 is 1. If I remove 3 electrons, I will get 3d3, 4 is 0. Okay, so how many unpaired electrons we have here? 3. Number of unpaired electron is 3. If I go for the second complex, oxidation state of iron is +2. Okay, it is +2. So the configuration of iron is 3d6, 4 is 2. And if I remove 2 electrons, I will have 3d6, 4 is 0. 3d6, 4 is 0. So the number of unpaired electron is 4. If I go for the last complex, zinc complex, oxidation state is +2. Configuration for zinc is 3d10, 4 is 2. If I remove 2 electrons, I will have 3d10, 4 is 0. So now you see, first is having n is equal to 3, second is having n is equal to 4, third is having n is equal to 0. So the one which is having the highest n value will have the highest magnetic moment.
Hello.
Okay. Clear? So somebody is speaking. Anybody wants to say anything? JNV Anam students, you want to say something? Okay. So the correct answer is the second complex. Okay, second complex, iron complex has the highest magnetic moment. Okay. So 1 and 2, 1 and 3, they are wrong. So I hope this question is clear to all of you. So now we'll go for the crystal field theory. CFT. So the learning objectives in this theory are the postulates of crystal field theory and octahedral splitting, tetrahedral splitting, then color. We are going to discuss about the color. You see here, valence bond theory did not give any information about the color, but here crystal field theory is giving the information about the color of the coordination complex. Okay. So now
I have a doubt.
So now let's start with the postulates of crystal field theory. So what is the postulate number 1? Before moving on to the postulate, we need to know the shape of the 5d orbitals to understand this theory. Okay. So we do have 5d orbitals, right? So dxy, dyz, dzx. So these are the first 3 orbitals. So for these first 3 orbitals, all the 4 lobes will be in between the axis. Okay. So they are all in between the axis. This statement is very important. Okay, in one of the previous year, they have asked this. So the lobes for the first three orbitals will be in between the axis. Okay. So now the fourth and fifth orbitals are dx square minus y square and dz square. For these two orbitals which has the square, the lobes are present along the axis. Or I can say that they are all on the axis. They are all on the axis. If this is the axis, the lobes will be on the axis. Okay. In the previous case, the lobes were in between the axis. Okay. I hope this is clear. Do you have any doubts in this? Can you all able to differentiate between along the axis and in between the axis? So here you see in the picture for dz square you see the lobe is on the z axis along with some donut kind of shape, which is also an electron cloud. Okay. So for the first three in between, for the last two, it is along the axis. So you should know the shape of these orbitals first. So you might have studied this in class 11 in the structure of an atom lesson. Now I have just recalled it. Okay. Now let's go for the postulates. So postulate number 1 is crystal field theory is considering the metal ligand bond as an electrostatic bond. Okay. So it is considering the model as an electrostatic model or the bond between the metal and ligand as an electrostatic bond. Electrostatic means ionic. Okay. Metal ligand bond is ionic. So this is postulate number 1. Okay. So next coming to postulate number 2. Ligands can be of two types. One is the ligand can be a point charge. Point charge means sorry, it can have a charge, the negative charge, okay, like Cl minus, we have Cn minus, right? So it can have a negative charge or it can be a dipole, point dipole. Dipole means we have water, which is a neutral ligand, and we have ammonia, NH3, right? So in case of water, these two are hydrogen and this is an oxygen. Okay. So the ligands can be of two types. One is anionic ligand, which is considered as a point charge, and the other one is a neutral ligand, which is called as a point dipole. Okay. This is point number 2, postulate number 2. Now coming to the third thing. Metal and ligand. We have this and the ligand is donating the electrons to the metal. So there are two things happening here. One is electrostatic attraction due to positive and negative charge. Metal is having the positive charge and ligand will have the negative charge. So there will be attraction. At the same time, we will also have repulsion because of the electron present in the metal and the ligand. So there is some attractive force between these two and also there is some repulsive force between the electrons present inside the metal. So metal orbitals will also have some inertial electrons. Okay. So that electron will repel with the electrons present in the ligand. Okay. So actually the metal is positively charged only. In all the cases, in iron case, we have seen no Fe2 plus, Fe3 plus, zinc 2 plus, chromium 3 plus, and many other metal ions, if you take, all will be in the positive state only. But we also have some electrons inside the metal, right? So that electrons will get repelled with the ligand. Okay. So there are two forces acting here, attraction and repulsion. So because of these two, the energy of the system, because of this, due to this ligand field, the energy of all the 5d orbitals is increased. Okay, because of these two forces. So one will try to attract, but the other force will try to take away the ligand from the metal. Ligand will try to come and form the bond with the metal, but at the same time, ligand will go away also. So because of this, the energy of the d orbitals is raised. Okay, it is increased. Okay, so this is the free metal atom or a metal ion. So for a free metal atom, all the 5d orbitals will be in the same energy. So the orbitals which are actually having the same energy are called as degenerate orbital. Okay, here you see, if energy is increasing like this, all the 5d orbitals are having same energy. Okay, and this is the symmetrical field of the ligand. Symmetrical field means all the ligands, they are trying to approach the metal atom, metal ion. Okay, so at this point, what happens when ligands try to come and form the bond with the metal, all the 5d orbitals will go slightly higher in energy. Okay, all the d orbitals will go slightly higher in energy. The energy is little bit raised. All the 5d orbitals energy is little bit raised. When does this happen? When the ligand tries to come in contact with the metal. Is it clear up to this for all of you? Shall I go for the next thing? Shall I go for the next? Shall I go for the next slide, students? Do you have any doubts till this? So initially we have a metal ion. For the metal, we have 5d orbitals. All the orbitals are of same energy. So when the ligand tries to come and approach the metal, all the orbitals are going higher in energy. Okay, why they are going higher in energy? Because of the attractive and repulsive force acting between the metal and the ligand. Clear? So if it is clear till this, give me a thumbs up or type yes in the chat box so that I can move on to the next slide. Crystal field theory is very important. Okay, so lots and lots of informations are there. All the informations are very important. Students, shall I go for the next thing? Thumbs up. Okay. Thank you. So I'll go for the next. Now you see. So there are two fields. One is octahedral field. So octahedral means you all know, right? 6 ligands will come and form the bond with the metal. So if we have 6 ligands or 6 donor sites in the to the metal atom, we call that system as octahedral system. For octahedral field, among the 5d orbitals, 3 will go lower in energy and the 2 will go higher in energy. The first 3 orbitals will go little bit lower and the last 2 will go little bit higher. Okay, this is for octahedral case. For tetrahedral means 4 ligands, right? So for tetrahedral field, the first 3 will go higher in energy and the last 2 will go lower in energy. Okay, so this is called splitting of the orbital. This is called the splitting of the d orbitals in presence of octahedral field and in presence of tetrahedral field. Okay, so now let's discuss in detail about each splitting. So postulates are over. Okay, now we are entering into the octahedral splitting. Okay, now let's see. Let's see the d orbital splitting in octahedral complex. So I'm going to take the configuration of a free metal ion first. So this is the configuration where all 5d orbitals are equal in energy. Now when the metal is surrounded by the ligand, what will happen? Can anyone tell me? When the ligands are trying to approach the metal, what will happen to these 5 orbitals? Will it go higher in energy or it will go lower in energy? What will happen to the energy of these orbitals? Yes, very good. Very good. Very good, Nagashri and Priyanka. So all the 5d orbitals, they are going little bit higher in energy. Yeah. Okay. So now in presence of octahedral field, the three orbitals will go lower. The first three will go lower in energy and the last two will go higher in energy. And we are calling these three orbitals as T2G orbital and this two as EG orbital. T2G means triply degenerate. Okay. T2G means triply degenerate. Three orbitals are in same energy here, no? So it is called as triply degenerate. And here we have two orbitals with same energy. Means doubly degenerate. EG means doubly degenerate. Okay. Triply degenerate and doubly degenerate. Got it? So these are the names of these two splitted orbitals. And we have the center point which separates these two. And that center is called as barycenter. So the center point of these two splitting of orbital is called as barycenter. Okay. And the distance between this, energy level, distance between this is called as delta O. So what is meant by delta? Delta means splitting. Delta means splitting. O means octahedral splitting. Okay, delta O means octahedral splitting. Okay, so now from the barycenter, if you go to the higher energy orbital, the value will be 3 by 5 of delta O. And if you come lower, it will be 2 by 5 of delta O. So this is the value. Okay, this is a splitting of d orbital in octahedral crystal field. And I told you delta O is called as crystal field splitting in octahedral field. And EG orbitals are increased by 3 by 5 delta O. T2G orbitals are decreased by 2 by 5 delta O. Got it? So these are the informations which you should know. This is very important actually. Okay, which you should know about the octahedral splitting. So we will also study some more information from this part in the upcoming slides. So for now, this is enough. So do you have any doubt from this slide? Do any of you have any doubts from this octahedral splitting informations which I given you in this slide? Is everything clear for all of you? So type yes or type it is clear or give me a thumbs up. Yeah, very good. Okay, students, I will move on to the next. Next slide is about the spectrochemical series. So why I have brought this spectrochemical series here? So we have a series, okay, in which the ligands are arranged according to their strength. The ligands are arranged according to their strength from weak field to strong field. Okay, so this end is actually the weak field end and it slightly increases. And here we have the moderate part and that last, if you see, this is the strong field end. So the ligands are arranged in the increasing order of their field strength. Okay, and they are giving rise to a series of ligands. We call that series as spectrochemical series. What is spectrochemical series? The ligands are arranged in the increasing order of field strength called spectrochemical series. Okay. So in the strong field end, if you see, the very first strong field ligand is CO. Okay. And next comes Cn minus, ethylene diamine, NH3, EDTA4 minus. So till this, they are all strong field ligands. Okay. All these five are strong field ligand. So strong field ligands, what they will do, they will create more crystal field splitting. Strong field ligands, what they will do? They will create more crystal field. The orbitals are getting splitted up, no? So 3 below and 2 above. So they will create more splitting. The energy gap between those two will be more. Okay. So if we talk about weak field ligand, weak field means from I minus till OH minus we can take. Till OH minus. Okay. So the other three are actually moderate. So till OH minus we can call as weak field ligands. Okay. So these ligands creates less crystal field splitting. These ligand will create less crystal. The energy gap between the two splitter orbitals will be very, very less. Okay. So strong field will create more splitting. Weak field will create less splitting.
What dimensions, madam?
Somebody is speaking, no? Students, do you have any doubt? If you're having any doubt, you can raise your hand or you can ask your doubt in the chat box. Okay. Yeah. Yeah, now let me go for the next. Now let me go for the complexes, D1, D2, D3, D4 type of octahedral complexes. We'll go for it. We'll directly go for the complex. For the complexes which has 1 electron, 2 electron and 3 electron in their d orbital, the diagram will look like this. You see, I'll go for D1 first, okay? So this is for D1. So if only 1 electron is present in the d orbital for some complex, first of all, it will go a little bit higher in energy, then it will get splitted up, okay? And that 1 electron will go and occupy the T2G orbital because electrons are arranged in the increasing order, right? So if an energy will increase like this, so first of all, the lower energy orbital is getting filled, which is T2G. Okay. And if I have two electrons, you see here, the two electrons are again getting filled in the T2G. And if I have 3 electrons for D3 complex, I will have 3 electrons now. So those 3 electrons will come and again occupy the T2G. According to Aufbau's principle, electrons has to get occupied the lower energy orbital first and then only it has to go to the higher energy orbital. Okay, this is the case till D3. If I go for D4, what do you guys think? If I go for D4 complex, if I have 4 electrons, all the 4 electrons will go little bit higher in energy, no? So where will this 4th electron go? Will it go and get paired here in the T2G or will it go to the EG orbital? Where will it go? What is your answer? Very good, Nagashri. Priyanka is saying it will go to T2G. Pallavi is also saying the same. Nagashri is saying if it is a weak field ligand, it will not pair. So you mean it will go to EG, Nagashri? If it is a if a weak field ligand is present, the electron will go to EG. Is that what you are meaning? Yes? Okay, good. That's great. That's great. Priyanka and Pallavi, it will go to T2G. But when you know, when the strong field ligand is present, I will come. I will show you the picture. Okay, I will show you the picture. You see here. So we have 2 chances. Slower energy is needed to split the orbitals of T2G level. Manasa, I am not getting your question, my dear. What you are trying to say? Slower energy is needed to split the orbitals of T2G level. No energy is required. The orbitals automatically, they get splitted. There is some separate story that why only these 3 is coming down and the other 2 is going up. Okay. So all the dxy, yz is the first 3 d orbitals, if you see, the lobes are in between the axis, no? So the ligand will approach along the axis. But these lobes are in between the axis. So what will happen? The repulsion will be less. The lobes are I'll give you the reason. Listen. So this is the lobe, no? For first three, dxy, dyz, and for dzx, this is the picture, right? So this is x-axis and this is y-axis. This is the metal orbital. But the ligand will come with its electron, right? So it will come along the axis direction. It will come along the axis direction. So the ligand will come here and the lobes is present here. So the repulsion is minimized for the first thing. That's why it is going lower in energy. Okay. But for d x square minus y square, this is x-axis and this is the y-axis. For dx square minus y square, the lobes are in between the axis, right? For dx square minus y square. So when the ligand comes along the axis, what will happen? Already the electrons are present here. The lobe is along the axis. Ligand is also approaching in the same direction. So they will repel with each other. They will repel with each other. The ligand orbital and the metal orbital are on the same direction. So they will repel with each other. And because of this, the energy of the last two orbitals will raised. And that's why Eg is going up and T2G is coming down. Is it clear for Manasa? Can you able to understand? I hope it is clear. If you have any doubt, still you can reach out to me. Did I clear your doubt, my dear Manasa? Okay. Okay. Fine. Now, what will happen? What will happen, you know? What is this? What I was saying? Yeah. For D4 complex, we have two chances. Okay, two possibilities. So in one case, the fourth electron is going to the Eg orbital. And in the second case, the fourth electron is going to the T2G orbital and getting paired up. And this is the separation. Delta O. Delta O is the splitting, crystal field splitting energy. Delta O is called as energy separation between the two orbitals. Along with this, we also have one more term which is called as pairing energy. Pairing energy means the energy required for the electron to get paired up in one orbital. Okay. So if this electron wants to get paired up with this electron in that orbital, it requires some energy. So that is called pairing energy. Okay. So you keep these two terms in your mind. One is crystal field splitting energy and the other one is pairing energy. Okay. So now I will come to these two types of ligands, weak field and strong field ligands. So what we have studied, weak field ligands will create more splitting or less splitting? Weak field ligands will create more splitting or less splitting? Just before few minutes I have discussed, no? Yeah. Yes. Good. So it will create less splitting and strong field ligands will create more splitting. Okay. Weak less, strong more. Now, coming to weak field case, since the splitting is very less, since the energy gap is very less, means the delta O is very less, delta O splitting is very less compared to the pairing energy. The electron will enter into the Eg orbital. The gap is very less, so the electron will enter into the Eg orbital. In the other case, the splitting is more. What is splitting? Delta O. Delta O is more than the pairing energy. Then in this case, the electron will not jump into the higher energy orbital since the gap is very high. So they will occupy, the fourth electron will come and occupy the lower energy T2G orbital itself. Okay. So this is the case. So here the splitting is very less and here the splitting gap is very high. So here the electron is getting paired up here itself, but here it is going to the Eg orbital. Okay. So if the electron goes to the Eg orbital, we call those complexes as high spin complex, and if the electron is getting paired up in the lower energy orbital itself, means it is called as low spin complex. It is called as low spin complex. Is it clear up to this? So this is all about the octahedral splitting. If we have strong field ligands, electrons will get paired up in the T2G itself because the energy gap is very high. So the electron will not take this much of energy and it will not go to the EG orbital. But in case of weak field, since the gap is very less, the electron can go easily to the higher energy orbital. Okay, so you should know this point. In case of weak field, pairing energy is greater, and in case of strong field, octahedral splitting is greater. Okay, here high spin, here low spin. So all of you must keep all these informations in your mind, and you have to apply all these things in your exam. Okay, so any doubt for anyone in octahedral splitting? Shall I go for the tetrahedral splitting? Say yes or no. Say yes or no, students. Yes. Okay. I want all of you to give me the reply, but why you guys are not giving a? So we'll go for tetrahedral split. Same thing. Okay. Concept is same only, but there is only one small change that I will tell you. Okay. So for the free metal atom, for tetrahedral complexes also, all the 5d orbitals will be in same energy, and in presence of the ligand in the spherical crystal field, they all will go a little bit higher in energy. Now for tetrahedral complexes, what will happen? The E will come down. The last two orbital will come down, and they are called as E orbital. Here we should not say EG. Okay, it is E. Clear? And the first three, XY, YZ and ZX, they will go higher in energy. And we call all these three together as T2 orbital. It is not T2G, it is T2. In case of tetrahedral, we should not use the letter G. Okay, E and T2. Now the gap between E and T2 is called as delta T. Why EG not? So why we are not using the term letter G is actually this T2G, EG, T2E, all these are symmetrical, what to say? They are symmetry elements. They are symmetry elements. So which is actually the out of syllabus for you. The symmetry elements you will study if you are taking chemistry, MSc chemistry, okay, as your subject. So there you will study about the symmetry elements. So according to that symmetry element, G is called as gerade. Okay. So it is called as gerade. So it is out of your thing. So for now, what you do, what you keep in your mind, you for octahedral, we have to use G, and for tetrahedral, we should not use G. So this is the point you have to keep in mind for now. So if I go into that symmetry elements topic, it is a very vast topic, and I need more than 10 classes to teach that. Okay. JNV students. Okay, fine. So what I was saying, the splitting. So here the splitting, you see it is called as delta T because it is tetrahedral field splitting, no? So it is called as delta T. And the above, the T2 orbitals are going higher in energy by 2/5 and E orbitals are going lower in energy by 3/5. Just the other way around. The previous case, above 3/5, below 2/5, and here above 2, below 3. Okay. This is splitting. Delta T is called as crystal field splitting. E is raised by 3/5. E is decreased by 3/5 and T2 is increased by 2/5. And at last you see, we have one relation. This is the relationship between delta T and delta O, which is very, very important. Delta T is equal to 4 by 9 of delta O. Means, which is greater? Delta O is greater or delta T is greater? Delta T is 4 by 9 of delta O. So it means delta O is greater. Delta T, Nagashri, it is delta O. Delta O is greater than delta T. Clear? Yeah. So this is about the tetrahedral complexes. Just you need to interchange the orbitals. That's it. Now we'll go for the color and the coordination complexes. So I think we can discuss this color topic in the next class. What do you guys say? Shall I teach this today itself or shall I teach this in the next class? Next class. Okay. So you all have class at 4 p.m., right? So you have to go for that, no? So if it is a last class, then I might have taught this. Since this is the first class for you and you have to go for the next. I'm closing. JNV Gadak students, I'm not going for color topic today. So we will do this in the next session. Okay. So thank you students. Thank you so much. So before ending up the session, I would like to launch a poll regarding the class feedback. So I have launched the poll. You guys can give your answers in the class feedback poll which I have launched, and then you can get ready for your next class. Okay. Thank you so much. Thank you so much. I have launched the poll. Please give your answers and then you can go. Thank you so much for attending the lecture. So all of you, please be on time for the next class, okay?